We are talking today about Tokio, Warp, and WebSockets. So, yeah, that's me. Hi, I'm Stefan. I have the worst Twitter handle on the planet. It's that parrot. So if you are into Monty Python, you maybe know what it means. If you aren't, don't worry. It's 60 years old or something. And today I want to talk to you about Tokio, Warp, and WebSockets. This is so I've spent a lot of time trying to learn async, trying to teach async in Rust. It's interesting. It's very different to what I'm used to from other programming languages, but also once you get it, it's really one of those mind-opening things. And I want to talk about at some other point. Now I want to talk about an actual application that I wrote with async in Rust. I use the Tokio framework for that. So Tokio is fun because if you've done anything async or anything web related in Rust, chances are that you have stumbled on Tokio in one way or the other, either by seeing some hash Tokio : main thing. Maybe if you deploy the Lambda on AWS Lambda or something in Rust, then you use that because the AWS Lambda runtime uses it. Or if you've written a web server, be it with Rocket, if you used Rocket, which was one of those talks that we had here in Rust Linz very early on, then you've used Tokio, even if you didn't know it. I think also Actic, so basically any web framework out there is based upon Tokio. It's a multi-threaded runtime for executing asynchronous code. It has an asynchronous version of the standard library and a large ecosystem of libraries. There are some alternatives. Glomio is one that I just found out about recently. Async standard is, I guess, the other big alternative to having an asynchronous runtime for Rust, which is honestly one of the better ones to learn async because the surface is a lot easier to understand because Tokio can get very big very early on. But if you reach one point where you are working on the application layers, usually stuff is mostly done in Tokio. Why do we need a multi-threaded runtime for executing asynchronous code in Rust? So Rust gives you all the primitives for writing asynchronous code. It gives you futures to write something that is executed at some point in time and returns a value. It gives you async and await to have syntax sugar to work conveniently with asynchronous code, but it doesn't give you a runtime to execute it. The reason is Rust wants you to choose the one that's best for your system. You could write asynchronous code for an embedded system and you might want not to use Tokio for that because Tokio might not be the right choice for that. Maybe it's async standard. Or maybe you have different concerns that you need to take into account. And for that, you have to choose your runtime. And the runtime is the one thing that takes all your futures, all the asynchronous bits and pieces, and executes it on a thread or multiple thread, depending on your flavor. So Tokio is not only a runtime, but Tokio is also an entire set of tools. It includes everything from low-level I/O up to type system-based service modeling and anything in between. So we have Mayo, that's short for Metal I/O, and it's some sort of abstraction layer on top of operating system events. Like, oh wow, there's a socket done. Please do something, dear application. That's coming from Mayo. It normalizes the I/O across all operating systems for apps that you build on top of it. Then we have the Tokio runtime, which is the heart of Tokio. It's the asynchronous runtime. It implements work stealing if it's multi-threaded. So you have a queue of tasks. Task is a unit of process in Tokio land. And you have a couple of threads that spawn workers which can work on those tasks, and they just pick a task from a queue, execute it if there's something to do, or put it back on the queue and produce results. So that's what Tokio does. It also comes with a rich standard library. They have async file I/O, async network I/O, timer schedules, all that jazz. That's all there in the Tokio runtime. And this is already great. And if you're at that level, you can pick and choose whichever runtime that you like. There are plenty out there. Tokio might be one of the most popular, but there's maybe others that are better suited for your needs. And then there's even stuff on top of that. And that's a couple of layers. First is Hyper, which is an HTTP implementation, a correct HTTP implementation for Rust, which implements HTTP 1 and 2 for both client and server, which is basically the framework basis for anything Exum, Rocket, Warp, Actix, you name it. That's all based on this package. We have the same thing for gRPC. It's called Tonic. It's also a layer on top of Tokio, which implements the gRPC protocol, and you can work with that. And all those protocol implementations get around the idea of a service, which is done with Tower. So think of it as a middleware layer, where you have different middlewares, different layers on top of each other. You can build a tower. And then you run a request through this tower, down to the bottom, you get a response, you run it up again, and then you can modify requests and responses like, oh, there's an HTTP response which I want to cheat zip, then you run through the cheat zip layer, and maybe you want to have a JOT token validation, then you run through the JOT layer, or maybe you don't want this to take really long, let's have a timeout layer so you can kill some of those requests if it's not worth working with them anymore. So this is Tower, and all those things build up, all the things that we see then are building up upon Tower. We also have a couple of packages that help us with the whole thing. Bytes is basically a synchronous reference counter mutex on U8. That's cool if you want to manipulate byte arrays across threads, and tracing if you want to monitor, if you want to send your data into Datadog or Dynatrace or whatever. So that's this part. Well, and on top of that, we also have frameworks. And frameworks like Exum, which is pretty new, which is from the Tokio team themselves. It's also in the Tokio organization on GitHub. And Warp, which is one of the Tokio maintainers, one of the hyper maintainers from Sean MacArthur, which I guess that's a pretty wild guess. So Sean, if you can see this, and if I'm totally wrong, I'm sorry. Warp is, I guess, inspired from a Haskell framework that's named similarly, and you can see that if we look into an example, it's very functional and very compositional and filter based, and I think it's beautiful. So I liked working with that a lot. But yeah, so those are a couple of frameworks, but there are others, and you can see Tokio basically anywhere. So one thing where I had to work a lot with Tokio is Deno. I'm using Deno in a couple of projects, not just as a runtime that I can install as a binary, but I use the runtime itself to work on a couple of JavaScript projects. More than 5,500 crates depend on Tokio, and that's crates, not applications. So it's really, really popular. All right, but what we're going to see Warp just in a bit. What Tokio also gives us, and that's very inspired, I guess, by Go, and how Go works in terms of communicating with Go routines, which is their version of executing asynchronous code, is channels to share state. And I want to quote Rob Pike, who said, if you run concurrent code, if you run things concurrently, don't communicate by sharing memory, like a mutex, like an RW lock or something. Share memory by communicating. So you get a couple of channels where you can send messages through, and you can pick it up from your other tasks. You have those independent units of executing things, and you send data in between them, and you're good with it. There are a couple of things, a couple of implementations in Tokio. There's MPSC, which stands for multi-producer, single consumer. So you have a lot of producers, many taskers can create value, and you have one consumer that gets them. One shot, which is just sending one value once, and then it's done, which is great for communicating back. So you can, for example, use this send the sender pattern, where you send something to your consumer, and you get the sender, where you can send back to the producer. So you can do this back and forth, which is great if you have some architecture where you have the web layer completely separated from everything else. This is where I use that a lot. Then you can communicate between two parts of your architecture without them even knowing from each other. It's just message passing. Watch and Brokers is multiple producer, multiple consumer, with a bit of different flavors. So there's a lot of stuff in there. So the tasks operate independently, and you can send messages in between to synchronize. And yeah, channel support sending a message from one producer task to one or more consumer tasks. One that we are going to see right now in an implementation, this is also available in the standard library, in standard sync MPSC, is multi-producer, multi-consumer. Send work to a task and receive the results of many computations. multi-producer single consumer channels have a capacity, but they're also unbounded variants. So this is the idea. You have many producers, you send it to one consumer. Alrighty, and those are many producers, but this also could be just one producer. So we have also one-to-one, but with multiple computations. Here's a little example. So I have, I hope you can see my cursor, because I don't have those fancy arrows to draw on the screen, but here I have an async function main. I create a new TCP stream. I connect to some server, and then forget this line. This is not so important. This is more important. I create a multi-producer single consumer channel with a capacity of 100. Okay, and then I create 10 Tokio tasks with Tokio.spawn, and I do that from 0 to 10, so 10 tasks in total. I clone the producer, and a clone from a producer just creates another producer. It doesn't create another channel. It just creates another producer, which means I have many producers that talk to one receiver, but I need to clone that so I can move that into this async move here. So this async block, which is a future. So if I write async move here, it creates a future that's being executed in the Tokio task that Tokio spawn does. And once this async, once this future is executed, I can send some data to this channel. And down there, I'm going to receive it. So this is also pretty nice. This is a Tokio stream. So this is some sort of asynchronous iterator. Even if you look at the trait definition, it's also very, very similar to an iterator, which is that you have an option that returns an item, but it's also something that's packed in a future, so you need to wait for it. So you can use it like an iterator, but it's asynchronous, so it runs somewhere in this whole task execution on Tokio. And yeah, so if I get some data here, I write everything out. And one thing that is important, this receiver returns none, so it's an option. Either I have a value, some value, or I have no value at all. And if I have no value, it returns none. But it only returns none if all the producers have been dropped. And this happens, if this block here ends from the async move block. If this move block ends, TX gets dropped because, hey, freeing memory, that's the ownership model of Rust. But the original producer is still available. That's why I need to drop it manually in this case. So I need to drop that. So the rx.receive returns none at some point, and I can stop the execution of my program. So this is one of those channel types that are available in Tokio, and this is also the one that I want to focus on today. So there are a couple of more, and there's great documentation out on all of them. But this is one that's interesting for what we are doing. Just in a second. Alrighty, and what I want to do is having a simple WebSocket chat, and this is a very, very stupid architecture diagram. I have a client, that's a browser up here, and I create a WebSocket connection to some server. So this is the world symbol for a server, which is a cylinder. I don't know why, but that's the world symbol for a server. And or is it for a database? I'm so sorry. I guess I totally forgot. But I'm creating a WebSocket connection, which is I have something to receive. That's Rx is for receiver, TX or TX is for transmitter. These are terms that come from broadcasting, actually. So from radio broadcasting, you have a transmitter, you have a receiver, and the abbreviations for that were TX and RX, and we carry them until today, even if we do either sockets or just channels or whatnot. So I have a user RX, which is a receiver, so I get messages in from the browser. This is the one socket connection, and I have TX where I can send back to the web server. And I do this for every client connection, for every browser connection that establishes a WebSocket to the server. Once I get a message, what I do is I send this message to every user, and I create an MPSC channel for every user. So every user has the possibility to send messages to one or more receivers, to one receiver. So I broadcast this to every TX that I have for every user that is connected. This message goes out through the channel. and it comes in on whatever receiver it is, and it goes back to the user TX, to the user transmitter. So this is a sort of round trip that I do. This is everything that I do with the WebSockets. I establish a connection, and I'm using channels so I can communicate between all those connections that I have by keeping track of all the senders and sending out stuff. Alrighty, and this is what we're going to see right now. Let's remove my presentation and give me a second. Let's go to Visual Studio Code. And that's the WebSocket implementation itself. That's Warp. And as you can see, it's very busy. It's very, very busy because the moment you want to abstract a lot of stuff with for web servers or whatnot, you end up with a lot of types. And if you end up with a lot of types, you get type annotations the size of War and Peace or something. So really, really huge. Nonetheless, for right now, so that you can scan this and see what's happening there, let's remove the inlay hints. And if you learned one thing today, that you can remove the inlay hints. It's a little bit less busy to look at. Okay. So what I'm doing here, I create a new Warp server, and Warp is funny because you are connecting bits and pieces to create routes and to create callbacks for that or stuff that needs to be executed, and it's then and or. So it's just connecting little filters together, and then you have a big filter tree. And when a request comes in, it gets filtered through, so it finds the right and the last stuff to execute. And this is very functional. This is very Haskell-ish, if you will. But it's also a lot of fun to use. So especially if you have a little love for functional programming. Alrighty. So let's start with something easy. One that I do, which is great for starting a web server, is serving a static directory, a directory with static files in it. And I create a new binding where I say, okay, this is warp, ::fs, : directory, serve everything from this folder. If it's an HTML, serve an HTML. If it's a CSS file, serve an CSS file. And that's about it. So that's the easiest that you can do. Here I have a route that does some more interesting stuff. So I create a path that's called hello, which means I can do /get/hello. So this is a route that I'm creating for that. And let's say, okay, you have an optional argument, an optional parameter, and I create this parameter up there. I say, okay, hey, I want to have a string parameter, and if it is some, return it. If it isn't some, return at least none. So I get an option back. An option which either have a value or I have no value. And this is an optional parameter, how I declare it in Warp. And so I can say, okay, for this hello path, have this optional argument, have an optional parameter there where you can send, something like that, or Stefan or whatnot. I also say, okay, after this, let the path end. So it's not possible to write /hello /warp /something. This is not a valid route. I let the path end after an optional argument. And this is one filter that I create for this route. And then I say, okay, everything that comes into that filter, let's map it to something that I want to execute. And what do I get? I write a closure here. We heard a lot about closures today, I guess. So you know what this does. I get an optional string in there. And I say, okay, say hello to the name unwrap, or else say world to string. I guess I could just write unwrap or world. That should work too. I don't know why I did it that way. But this is how I create a hello route with an optional argument where it says either hello world or hello name, depending on what you do. And this is how you plug everything together. Here, that's also interesting. I have a 404 route, which means that for any else, so this is every other request that pops through, this is a filter that accepts it, create a new response, where I say, okay, my status code is not found, 404, and the body is just this 404 HTML file. And this is also a string that a function fs read to string which is also something that could error, so I expect it to work. And if this file isn't here, I get a 4 for my 404, and this is a very, very, very bad error message, but I was lazy, I guess. So result of 404, I have some files, I have the hello route, and now I combine them. So I say, okay, wait for the chat. I'm going to talk to that in a little bit. So I say hello, or files, or 404. So those are, this is the order that of priority. So I say, okay, hey, the hello route goes first. If I have anything there, that's my dynamic API, execute this. If this gets filtered out, so it's not part of this, select the file. If this file isn't available, go to the 404. And that's how I concatenate all those filters to each other. But I also have this chat here, and this chat is funny. This is the chat route. So I say, for the WebSocket, route, for the path get WS, try to create the WebSocket out of it. Try to do a WebSocket upgrade. I don't know if you know how WebSockets work, but WebSockets is basically talking over HTTP if they speak HTTP, and then sending this upgrade header. I say, hey, do you speak WebSocket? And then you get either OK back or not OK back. I say, yeah, I speak WebSocket. Then they say, okay, let's upgrade our existing HTTP connection to a WebSocket connection. And now we can send back and forth packages. That's what it is. Basically, it is a little protocol on top of TCP then. The TCP connection stands open, and you can send packages back and forth, and the browser knows how to interpret them. The server knows how to interpret them. That's what it does. What I also do, and that's also funny, I add some users there. And users is this here, is this little data structure that I have here. Users default, that's a very simple data structure. It's basically an atomic reference count on a read W log on a hash map where I store multi-producer, single consumer senders. That's a huge type. Basically, it's a hash map of channel senders that I store with a user ID. And I just created a little type so it's easier to manage for me. And what I also do through some shadowing, I say, okay, if users, I want to create a filter out of it, a filter that I can use with Warp, which means I say, hey, for anything that bubbles through here, map it to users.clone. Since it's an atomic reference counter, I get another atomic reference that I can work with. And suddenly I have here in my chat users available as an object. So I can, this is how I map data structures into this filter chain of Warp, where it just bubbles through, and then I can use the data in there. And this is what I do. So what I get is I get a WebSocket plugin from Warp. I get the users to say, if this WebSocket upgrade is successful, so on upgrade, I have an actual WebSocket, and then I want to call this connect function with the socket and with my users. So this is what's going to happen here. That's a mouthful, that's a lot. And this connect function, this is what I'm going to implement with you right now. So here again, combining everything, then I'm serving the routes, I bind it on a socket address, and I wait for that. And here, oh, there's a to-do function. So this is now something that I have to do with you. Alrighty, so let's toggle the inlay hints again, because I need them when developing. The first thing that I do, I create a new user ID. Let my ID, I have one thing up there, that's the next user ID, which is an atomic usize, which means it's a thread-safe usize that starts at 1, and I can increment it across threads and across Tokio tasks, of course. So I say, my ID is next user ID, and then I have something like fetch, add, where I say, okay, basically take this one and add one to it. And how do you add one to it? I don't care about race conditions or whatnot. I say, hey, do it in a relaxed way, so increment whenever you can. Because, hey, everything that I want to get out is the next user ID. I don't care if somebody is there in front of me. Absolutely not something that I need to do. So let's print out that I have welcome user, that I have a new user. Alrighty, what I do then? So I have a WebSocket connection established. That's great. Sorry, it's my ID, and here I say it's ordering. Sorry, better. Okay, so I have a WebSocket established. Now I want to get the transmitter and the receiver. So I want to get something where I can read from. Want to something where I can write to. And I call that, like in my architecture diagram, user TX, and I need a mutable user RX, which I do from WebSocket.split. And this is splitting is always pretty funny, because if I go to the definition down there, it's split, and then I have here split again, split, and again the split. So basically, long story short, it's still one connection, but I get a reading reference and a writing reference to the same socket that I can use differently, and I need to use them differently so I can move those parts safely across threads, across tasks, etc. So this is the idea why I want to call split there, but I don't want to use the same socket for reading and writing, because I want to do different tasks with. So that's the connection, something to read from, something to write from, between browser and server. So, and what I want to store is I want to then use channels so I can communicate between all the existing users that are there. So I create something for the users to communicate. So that's TX and RX, and here I create a multi-producer, single consumer. Let's create an unbounded channel. I don't care about bounds in that case. So if you get too many requests, it errors. That's bad. But usually for that, what I'm doing here, that's okay. What you also see here, the types are unknown. TypeScript, Rust. That's a fraud. Rust can't infer the type yet, but it will when we move forward. So bear with me. And what I also create, so this is a sender and a receiver for the channel, so I can send stuff out. It gets received to the other side, and this is the way how I want to communicate between channels. What I do with RX, because I get a couple of convenience functions with it, I say let's create an unbounded receiver stream out of that receiver stream. And now I have an unbounded receiver stream where I can simply use it to forward everything that comes in to something else. And this is what I'm doing right now. So I create a new task. I spawn a new task. So this is the one thing that needs to be asynchronous. This is every time something happens, I want to forward everything that comes in from X. So these are the messages that come from others, and I want to send it out to the WebSocket to the browser. So this is what I'm doing here. So I say forward everything to user TX. So every message that comes in from my internal users, send it out to the WebSocket to the browser. This is what I'm doing here. And suddenly I also get type annotations, right? So now it's now a message, etc. So this is what we get here. One thing that I need to do as well, I want to add the new user. So I had created a new user, and this is why I want to store them. And what I'm storing here is, say, users.write. I get write access. Wait. It's an asynchronous operation because I'm using. Why is it an asynchronous operation? Because I'm using the Tokio sync RW log and not the one from the standard library. This is because those RW log write guards are not thread safe. They can be thread safe if you know how Tokio shuffles or async shuffles those tasks in between across the wait blocks. But that's a lot of stuff for you to do on your own. That's why Tokio provides you with an abstraction layer on top of it, so you can use it easily within your Tokio applications. And you can have everything like mutex as well, or TCP listeners or file listeners. There's always a variant of that works really well with the runtime. Also with the same API, which is nice. The only thing that you need to do is wait for it. And once you get it, let's insert based on the ID that you have this one sender. So what I'm doing here, I store all the senders, all the transmitters for all my users in this bookkeeping data structure. That's what I do here. I'm not using a mutex because mutex means it's logged for reading and writing, and RW log means once I lock it, others can still read, which is interesting for broadcasting later on. So it's a little bit fast in certain scenarios. Okay, let's do that. Now I have this here as well. Okie dokie. So now I created the connection. I said, okay, everything that if I have a message internally to broadcast, send it out to the WebSocket, store the sender, and now I need to use the sender. Now I need to broadcast stuff. This is done by listening to messages from the WebSocket incoming. Let's say I have some result, which is user rx dot next. So it's a stream. It's an asynchronous stream. I get little messages in. I wait for them, and once I do that, let's broadcast this message. So I create a little function. Broadcast, it's an async function, broadcast message. The message is of type message. That's what comes in from a WebSocket. So you see warp filters, WS for WebSocket. That's a WebSocket message. That's great. And I want to have a reference on my users. And then I say, okay, for if let okay string message or str message. I don't need that, I guess. Do I need that? I don't know why I need that. I guess this is an operation that could fail, but I want to have it because I want to send strings. I want to check if this is a string message. I guess this is what I want to do. It's been a while. So if this is a string message, let's get all my users from the user data structure. And it's an async stream, so I have some sort of iterator. No, that's an actual iterator because I'm now accessing the Hashmap. So I'm reading the RW log, I'm accessing the Hashmap. Now I have an actual iterator, and I say, okay, for every sender that I have here, send a clone of the message, and failed to send message. So this should be it. That's the broadcast message stuff. That's great. And here I say, okay, broadcast message, and the message is the result, and unwrap it. So I expect failed to fetch message. That's also a result type. Alrighty. Okay, that looks good. I'm already broadcasting. Oh, I have some troubles here. I guess I need to have a semicolon in there. Now we are good. This one, oh, okay, that's an asynchronous function. So I definitely need to wait. Thanks to Rust Analyzer for letting me know. Okay, now for the last part, this is something that I don't need. I want to also write the disconnect message. So if something, if one of the users is gone away, I want to disconnect them. Let's hit disconnect the user ID from users. Yes, yeah, okay. First of all, print line goodbye user ID. There you go, and say from users. Users of blank, so you can have it centered in the screen. For users, write or wait, remove my ID. Because it's a Hashmap, I can just call remove there. Oh, that has been something. Where do I put the disconnect now? So how do I say that I disconnect the user? And this is great. This is great because we have here an asynchronous stream, and this one returns either a result or it returns none. And when does it return none? It returns none the moment the connection drops. The moment the connection drops, this next returns a none, which means this whole while block ends. I don't get any messages anymore. I can safely disconnect. Yeah, that's it. I can safely disconnect my ID from the users. And I, of course, need to wait that too, because it's an asynchronous function. And what I like especially about this is that first, bookkeeping, that's establishing a connection, reading and broadcasting messages, disconnect. That's sequential. That's a 4-step solution to having WebSocket application. And the only thing that I need to do as synchronous is this particular line. I say, okay, everything that comes in from X, forward it to user X. I don't want to have that in my synchronous code, right? What synchronous? In my sequential code. I want to have that somewhere else. This is a standard task. Work on that. Just forward that. I don't care. The rest is bookkeeping, establishing a connection, reading and broadcasting messages, and disconnect in the end. And this is the only thing that I need to put aside. This only little Tokio spawn. Of course, I have lots of awaits in there, which means there's lots of little tasks, because basically every await is some sort of checkpoint for us to say, okay, this is one package, one part in this future state machine that I can execute independently. This is with every await block that there is. But everything that I need to shove aside, which I need to not have in my sequential flow of code, is this line. That's everything there is. Couple of live coding. Let's see if it works. I don't know. The old one worked. Look at that. There you go. Let's see. Cargo run dash release. Okay. I have a server down here. Building. In the meantime, I'm opening up another connection. And what I'm also opening up is for you to look at. That's an index.html file. It does nothing but loading a Mainjs file. The Mainjs file is very, very simple. It creates a new WebSocket connection. That's that. It opens it. That's great. It's connected. On message, it says, okay, receive the data and put it in some text content. And on send, it sends some data. That's all there is. It's nothing fancy at all. Just getting messages, sending messages. Not even jQuery in there, because I clopped it together really, really quick. Okay, back to the terminal. Okay, I have a running server at this URL. So if I say curl localhost 8080 hello, then I get hello world. If I do it with hello Rust Linz, I get hello Rust Linz. Oh, that's great. That already works. Now let's see what happens if I want to curl localhost. Static file. That's great. You can see that I tried it with Actix first. Now I switched to Warp. That worked a little better. So let's do even more stuff. Let's open up a browser. Let's go to localhost 8080. And say hello. Oh, I didn't implement return. Hit send. Hello. Cool. Oh, that's great. I just got everything that came up from here down there. That's super great. Via a server round trip. That's easier, but it's even better if I create another browser window down there and say, how are you? If I click send here, let's see. Ta-da! It's here as well. I'm great. I just coded a web server, a WebSocket server, live on stage at Rust Linz. Alrighty, and that's about it. That's the demo. So in the end, one advice that I can give you if you want to develop a WebSocket server on your own, that's a very basic demo of establishing that. Tokio gives you a lot of stuff to wire everything together, to plug something in and send messages via channels and opening connections. So this is all part of Tokio. Everything that happened after WS, after I had this WebSocket connection established, is pure Tokio. It's not part of the framework. And this is also the reason why I was able to do that. Because those frameworks like Warp and Axum, they build on top of those Tokio primitives, which means everything that they can't provide on their own, you can do yourself with those Tokio libraries. If you have a web server like Actix, or if you have a web server like Rocket, a framework like that, stuff like that becomes, in my experience, increasingly harder because they are opinionated. They are opinionated, which also means that WebSockets need to work according to their opinion, which is great. You know, you want to have an opinionated server because it moves you fast. It brings you up to speed, but also you need to wait until they decided on their opinion on those topics. I guess WebSockets is on the roadmap for Rocket, which is great. I'm looking forward to that. I'm really looking forward to that, how they solve it, because it's I think this is a challenge. I tried to implement it with Hectics and needed to work with the actor model, which was way too tough for me to understand. But I think it's doable there as well. There are some tutorials out there. I found this to be the easiest version. And I think if you use Axum, which is a declarative web framework from the Tokio folks, you end up at the same point where you suddenly get all those primitives in your hand, where you can create channels, where you can create sockets, and you can split them, and you can write them, and you can read them, and then you can do all the message passing around it. So that was my talk.